Welcome back to the workshop. We want to continue taking a look at section 1.4, algorithms and their efficiency. We already took a look at an algorithm for evaluating x to the n, and in this video, we'd like to consider an algorithm for evaluating a polynomial. First, let's take a brief look at what we saw in the previous algorithm. So we saw that there was a while loop, and in a while loop, we do the things between while and end while until the condition is not satisfied. So while this condition is true, we do these two things. Okay, check it, go through the loop, and then go back to the beginning. Check it. If it's true, still true, we go through the loop and go back to the beginning. And we continue that process until this condition is no longer satisfied. So you would have a real problem if there were no direction to increase the value of k. That would be very bad. If there were no direction to increase the value of k, k would always be less than n, and you would be stuck in that loop forever. That would definitely be a problem. All right, so we saw that in the process of evaluating x to the n, there are 3n minus 2 operations. So when we use the algorithm that we have here, there are 3n minus 2 operations that we have to do. That is addition, subtraction, multiplication, division, or a comparison of two numbers. Excellent. We're going to need to remember that as we consider the polynomial evaluation algorithm. And what we'd like to do in our polynomial evaluation algorithm, as we read it, we try to understand what it's saying. We want to go through an example at the same time. So for our example, well, let's read at least the first part. So this algorithm computes this polynomial given the non-negative integer n, okay, the power of the polynomial or the degree of the polynomial, and then all of the coefficients and the value that we want to evaluate the polynomial at. Okay, so essentially we're just inputting all of these things, just not as the polynomial itself, just telling it x on all the coefficient values. Excellent. Once we have that, then what this does is it uses s as the sum, right? So you can think of it as sum. We're going to add a bunch of things together. That's what we're doing when we look at a polynomial. We're adding a bunch of terms together. So you can think of it as sum. And then k is just our counter. And that counter tells us when we're done, when we've reached the end of all of our terms, right? Once it hits n, we know that we're at the last term. That's going to be essentially what happens. So what we want to do is we want to compute the values of s and k in the, let's see, I suppose while or when the polynomial evaluation algorithm is used to evaluate. And we'll go ahead and consider a pretty basic example here. So let's look at the example of, let's see here, quadratic 2x squared plus 3x plus 4. And we want to evaluate at x equals 3. All right, excellent. So there's 1, 2, 3 steps similar to what we had in the evaluation of x to the n. But in this case, it actually has an evaluation of x to the k in here. So that's a little bit of an issue there. So things are a little bit different, right? We don't have x to the k as an elementary operation. So that will make a difference on our when we determine the complexity of the algorithm. All right, so an example here, evaluating. In step 1, what we do is we set s equal to a sub 0. So a sub 0 is 4. A sub 0 is 4, so s is equal to 4. And k is equal to 1. Excellent. So we're done with step 1. Step 2 is where we have a loop. So we check the condition. Is 1 less than 2? Yes, 1 is less than 2. So what we do is we replace s with s plus a sub k to the x k. And here k is equal to 1, so this is a sub 0, and this is a sub 1. So we have 4 plus 3 times x to the k. So we're looking at 3 to the 1. 4 plus 3 times 3 to the first power. Well, 3 to the first power is just 3. 3 times 3 is 9. 4 plus 9 is 13. Excellent. We replace k with k plus 1, so we get k is equal to 2. Now that we reach the end while, and we return back to the condition, that would either tell us to repeat the loop or kick us out of the loop. And that's this guy. So we have k is equal to 2 now. Again, the degree of our polynomial is 2, so that is n is equal to 2 in this case, right? N is equal to 2. So is 2, the value of k, less than or equal to 2? Yeah, it's right, it's equal to. So here we did step 2, and we do step 2 again because the condition is satisfied. So we replace s with s plus this thing. So now we have 13 plus the coefficient, so 2 times x squared, and x is 3 here, so 3 squared. So we have 13 plus 2 times 3 squared. Well, 3 squared is 9. 2 times 9 is 18. 18 plus 13 gives us 31. And we increase k by 1, so k is equal to 3. And then we have, let's see here, we return back to check the condition. K is equal to 3, so is 3 less than or equal to 2? No, that condition is no longer satisfied, and that kicks us out of the loop. So we move on to step 3. Step 3 is simply output. Right, we still have s is equal to 31, k is equal to 3, and we output. Let's see here, p of 3 is equal to 31. Excellent. So that's the polynomial evaluation algorithm. It's really no different than what you might do to evaluate the algorithm using your calculator, right? You take the constant, and then you add the term before, and then you add the term before until you have all the terms. So it's just we're starting here and working your way to the highest power. And maybe what you do to evaluate would be to start at the highest power and work your way this way. It's the same thing, right? Start here and there, start here and there, but it's essentially exactly what you would do using your calculator. Excellent. So let's determine the complexity of this algorithm. So this one is a little bit strange. So the easiest way to think about this is what happens in each loop and how many times each loop is executed. So recall first, x to the k requires, so x to the n would require 3n minus 2 elementary operations. So x to the k requires 3k minus 2 elementary operations. All right, so we're going to need to use that a little bit later. All right. So each, well, the loop, so the loop is executed or completed. We'll say completed. The loop is completed how many times? Well, I completed step 2 2 times. And that's exactly the value of n. N is equal to 2. So I would actually have to do it, right? I take my constant, and then for x to each power, I go through step 2. So the loop is completed n times. In each loop, there are, so we have 1 addition, 2 additions in each loop. Two additions, and then we have 1 multiplication, and x to the k requires 3k minus 2 elementary operations. Excellent. And then let's see here. How many comparisons do we do then? Well, we do n plus 1 comparisons. Okay. The n plus 1 comparison. So n plus 1 comparisons get us out of the loop. Right, because I have to do n comparisons to run through the loop n times. And then the n plus 1, the next comparison, gets me out of the loop. So I do each of these things n times. And then I also do n plus 1 comparisons for each time that I execute the loop, and then the one time that it kicks me out. And then there's nothing after step 2. So what does that give us? So that's a total. Well, actually here, let's maybe phrase this a little bit different. That's 2n additions in the loop. Right, so by the time we're done, maybe I should say that's 2n total additions from the n loops, right? We go through it n times, and that's n total multiplications from the loops. And then we also have 3k minus 2 elementary operations. And so I would have to add, right? I can't just say that I have n times that, because it's, k takes on different values. So for k equal to 1, from 1 to n, because I run through the loop with k equal to 1, I run through the loop with k equal to 2, I run through the loop all the way up through k equal to n. So for each of those, it contributes 3k minus 2 operations for x to the k in the n loops. So what does that give us? That's total operations. Well, I've got my n plus 1 comparisons. I have my 2n additions plus my n multiplications plus this sum from k equals 1 to n of 3k minus 2 for each of the x to the k's that are evaluated. So I can combine these pretty easily, but this requires a little bit of work from calculus 1, right? In Calculus 1, there's a discussion on simplifying these summations. And if you need a little bit of reminder on that, we can do that. Let me first tell you what you should find. So we should find that this can be simplified to a total of 1/2 times 3n squared plus 7n plus 1 operations. So this is order n squared. And in order to evaluate this, in order to simplify that, you may need to recall, if I wanted to evaluate just this guy, k equals 1 to n, 3k minus 2, this is equal to the sum from k equals 1 to n. Let's see, I can distribute the summation over the subtraction, and I can pull the 3 out. So this is 3k minus the sum from k equals 1 to n of just the number 1. Once I have that, let's see, a couple more lines here. Well, I suppose just one. This is 3 times, let's see here, that should be n times n plus 1 divided by 2 minus n. Okay, so this thing right here simplifies to n times n plus 1 over 2. And that's something that you should be able to recall from Calculus 1. If you need a little bit of additional information on that, let me know, and I think I might be able to provide a video for you guys. So that's how we would simplify this, and then put that back into here, and it could be simplified. So overall, when we determine the complexity, this is the complexity of the algorithm. Okay, the complexity is a number, an expression that depends on n. All right, so that's all that I wanted to share for this video. We'll take a look at Horner's polynomial evaluation algorithm in our next video. Okay, and it's actually more efficient than the algorithm that we just looked at. So it's a little bit interesting. So I'll see you guys again back here in the workshop very shortly.